Thank you everyone for having me. Before I proceed, I would like to acknowledge the co-author of this study and my supervisor, Professor Yuan Tathar. My presentation is about FRP URAPs. And before I proceed further, let me define what is FRP URAPs. So it's a U-shaped band or strip which is bonded to the beam soffit and two side faces of the beam. And the purpose of this is to provide a beam as a shear reinforcement, to increase the shear reinforcement, and also provide anchorage for the longitudinal CFRP. So it serves two purposes. In the literature, there are several studies have been performed to investigate the anchorage effect and the shear effect of the FRP URAPs. But we couldn't find any comprehensive study in which the combined anchorage and shear effect has been investigated. So this research gap leads us to this question that can URAPs concurrently serve as a supplemental shear reinforcement and anchorage of Flexure CFRP and shear-deficient reinforced concrete beam. And this is the topic of my presentation as well. So in this presentation, I will discuss the objectives and scope of our study. Then I will discuss the specimen design, test matrix, test setup, experimental results, which is the core part of my presentation, and finally conclusion and future work for recommendation. So the two main objectives of this study is to investigate the combined shear and anchorage effect of URAP on reinforced concrete beams strengthened with externally bonded CFRP sheets. And the second objective is to make design recommendation for the use of the URAPs. To achieve these objectives, we conducted experimental study. And we developed a test matrix of 18 large-scale T-beam reinforced concrete beams. And we divide the specimen into three groups based on the amount of steel shear reinforcement. In each group, we have 6 specimens, and in each group, we also have 2 control specimens. One control specimen is unstrengthened, and the second control specimen is strengthened with only longitudinal CFRP sheet. And the remaining 4 specimens are strengthened with URAPs and FRP spike anchors. However, since this study is still going on, so we have, till now we have completed only testing of 12 specimens. So in this presentation, I will present the experimental results of only 12 specimens. For specimen design, we selected the T-beam section to represent the real condition of beam with monolithic slab. For the material, we use concrete with specified compressive strength of 4,000 psi, but the actual strength varies from 4,500 to 5,000 psi. We use grade 60 steel for the steel reinforcement, but the actual strengths are 61,000 for the number 2 rebars, which we obtained from a different source, and 70,000 for the remaining steel, number 9, number 6, and number 4. In reinforcement, we use 4 number 9 rebars as a tension reinforcement and 2 number 6 as a compression reinforcement, which correspond to a longitudinal steel reinforcement ratio of 2.2%. We used 16 feet long beams, and we tested these beams on a 14 feet span under the 4-point bending test. The shear span length was 5 feet, and these dimensions correspond to a shear span to depth ratio of 3.9, which fall in the cylinder beam categories. So these are the diagrams of the control specimen in each group. These are the unstrengthened control beam. So the first group has no stirrups. We only install stirrups under the point load to avoid local damages. The second group contains the control specimen with number 2 at 18 center reinforcement, which is equivalent to the ACI minimum reinforcement. And the third group contains number 4 at 18 center stirrup reinforcement. The strengthened control specimen is the same identical specimen, but we just only reinforce it with the longitudinal CFRP of 2 ply. We use 22-ounce CFRP fabric sheet. The properties after testing we obtain are in the slide, you can see it. And the width was a little less than the width of the beam, and you can see its dimension. For the beam designation, we use 7-letter nomenclature. The first 2 letters represent the number of ply in longitudinal CFRP. The next 2 letters correspond to the number of plies in 4-inch wide UREFs, and the last 3 letters represent the stirrups in the beam. Like for example, 2S8 mean number 2 rebar with 18 center. So this is the test matrix which I already discussed. So you can see we have divided the specimen into 3 groups. They are naming with A, B, C. In each group we have 6 specimens. 2 are control specimen and the remaining are strengthened specimen. And the specimen which are highlighted with green color, they are not yet tested, and this is the results of these specimens are not included. We also predict the capacity of the specimen in flexure and shear as well. In shear, we use, to calculate the actual strain, we use the modified compression field theory for the concrete and steel contribution, and for the UREF contribution, we use the ACI 440. And you can see the first group is totally shear control specimen, the next group is 5 specimen are shear control, and the last one is flexure control, and the last group is all flexure control. These are the diagram for the testing setup we have used for the testing of our specimen. We install beam in inverted orientation to facilitate the GIC imaging. We use 2 actuators, and the actuator loads are from the bottom side. So the top face is the tension face of the beam, and the bottom face is the compression face of the beam. On the left side picture, you can see the actual setup of the beam along with the DIC cameras and the lighting. On the right side, this is a 30-second video, and I want to play it, and in which you can see this is the strand map which we obtained after the post-processing the DIC data, and you can see the strain variation with varying load. So let me play. So we have 2 actuators. You can see the load variation. There is a slight variation between the actuator loads as well. And now the cracks are developing, and finally it will fail. And you can see the shear failure on the right side span. Along with DIC, we also use strain gauges to validate the DIC data as well. From DIC, you can obtain the displacement data and the strain data. But to validate the DIC data, we use strain gauges on the internal steel as well as on the UREFs and longitudinal CFRP. For the displacement, we install LVDTs at the mid-span, and we also install 2 LVDTs at the supports in order to check the support displacement as well. To calculate the principal strain and the shear span, we also install 3 LVDT rosettes on the beam web surface. But due to limited time, we are not including the data of the LVDT rosette in the presentation. Here I would like to briefly explain the shear failure types. So usually in experimental testing, we observe 3 failure types in shear. And these are based on the shear span to depth ratio. So once the A by D ratio is less than 1, so it is called deep beam failure, in which the compression strut crushes or the tension tie fail in anchorage. The second failure type is called shear compression failure, in which the A by D ratio fall in between 1 and 2.5. And the third failure type, which is mostly common in cylinder beam, this is called shear tension failure, or also called diagonal tension failure. In this case, the A by D ratio fall in between 2.5 and 6. In our case, our A by D ratio is 3.9, so we were expecting the diagonal tension failure. So from the experimental test, we developed 2 plots. One plot is the maximum shear versus the mid-span deflection, and the second plot is the maximum moment observed in the constant moment region and the mid-span deflection. Here I would like to explain that since we use 2 actuators, so we get slightly different forces in both shear spans. So the shear represents the force, the shear force of that shear span in which the actual failure happened. And the moment is the maximum moment in the constant moment region which we get. So this is the first beam, this is the first control beam of the group A, in which we don't have any shear reinforcement, and you can see the beam failed in shear, and this is a brittle failure. And we got around 36 kip load in shear. And this is the picture of the actual damage, in which you can see the shear crack on the left shear span, and the critical shear crack angle is around 35 degrees. This is the second beam. Because this was only reinforced in longitudinal CFRP, there is no shear reinforcement, so again we get the same result with almost same capacity and same failure type. And you can see here in this time that the failure happened on the right shear span, and you can see the shear crack here as well. This is the third specimen in which we installed the single ply of U-wraps. And now you can see there is an enhancement in the shear capacity of the beam, and the beam capacity is slightly less than 60 kip, but greater than around more than 20 kip greater than from the control specimen. And in this case, you can see the failure happened on the right side shear span, and you can also observe the two U-wraps are engaged during the failure. This is the fourth specimen, and this is the last specimen which we have tested yet. In this case, you can see we installed the two ply of U-wraps, but there is a slight increase in the shear capacity. I would say 5 to 10 kips. So, and again, brittle failure. But here you can also observe that the two or partly three U-wraps are engaged in shear failure, and the rest are okay. Now we are moving to the second group. In second group, we have the same specimen, but with number 2, 18 cm shear reinforcement. So now again we get a slightly higher force from the previous one, because this time we have the stirrups, and the capacity you can see is around 45 kip, and again it's a brittle failure. And this is the actual damage picture, and the shear crack angle you can see it's around 40 degrees. Again, with the same fashion, this is the second beam, but this is only reinforced with longitudinal CFRP. Again, we get the same response. Almost you can see the failure load is same, and failure again happened on the right shear span, and you can observe the shear crack angle. This is the third specimen in the second group. In this, we reinforce the same specimen with single ply of U-wraps. And now again we observe the capacity enhancement in shear as well. And you can see now the capacity goes to around 70 kip. In this case, the shear failure also happened on the right shear span, and you can see 3 U-wraps are partly engaged in the failure. This is the last specimen of the second group. Again, the same specimen with double U ply, and with same fashion like the previous group, we just only get 5 kip extra capacity. And this is the failure. Now we are moving to the third group, which are flexure control beams. Now this is the control specimen, and you can see a ductile failure. We are not considering the shear because this was the flexure control beam, so the flexure capacity of the specimen was around 350 kip feet. And in this case, we get the typical ductile failure after the yielding of the longitudinal reinforcement. Finally, we get crushing of the front. Now, this is the second specimen in the third group, and this is now longitudinally reinforced. So that's why we get enhancement in moment capacity and end as the load capacity. And because there were no U-wraps, so this specimen failed in typical IC debonding failure. This is the third specimen. Now this is reinforced with U-wraps, and in this case the U-wrap acts as an anchor, and now you can see the failure mood changes. The failure mood change from the FRP like you can see the UREFs are rupture, and the longitudinal FRP are rupture. This is the last specimen, and you can see in this case we just get the FRP debonding. In this case, we have summarized the same which I already discussed, the capacity. In this plot, we compare the maximum strain recorded in the using the DIC and the experimental strain gauge values, and they are quite similar. In this case, we also further verified, like using back calculation. We back calculate the strain gauge value from the experimental, and when we compared with the strain gauge value. In this case, we check the FRP UREF strain values. So you can see the shear contour specimen, we only consider the two UREF strain values, and they are higher than the ACI values because the ACI equation gives you very conservative. And these are the conclusion. In conclusion, we observed 70% increase in the shear enhancement, 28% increase in flexure, and we also increased 137% increase in the longitudinal strain as compared to ACI 440. And we also observed that the UREFs exceed the ACI effective strain value in on-shear critical. For future work, we recommend to investigate the effect of inclined UREFs configuration, also to investigate the performance of the pre-cured CFRP plates, and to investigate the effect of different CFRP properties of UREF and reinforcement. So at the last, I will acknowledge the contribution of the campus for funding this project. Simple strong tie for providing material and also money, and NEX for the sponsoring this session.